Hello, my name is John Mount. I'm a data scientist who works as a consultant and trainer at a company called WinVector LLC. And in this short video lecture, I'd like to explain one of the most important data structures in data science, the vector. Now, obviously, vector is a mathematical term, not a computer science term. And mathematicians tend to define things in terms of their properties. They consider implementation and irrelevant detail that may change, or two things with different implementations may fundamentally be the same thing when we consider them from the point of view of properties. Now, we're not going to use this graduate level definition in our day-to-day work. I really don't expect anyone else to do. But what it's saying is the primary property of vectors from a mathematician's point of view is additivity, that they expect to be able to add them. Now, mathematics can go up and down the scale. Here's a definition we really don't want to use from Bourbaki, that a vector is an instance of a K-module. Now, what this is a standard mistake in teaching, which I try to avoid, that we're going to define something that's going to turn out to be very useful, vector, in terms of something a little more obscure that is basically more fundamental from a mathematical nature, but unlikely to be known to the audience. So basically, something I hope you'll have intuition about, vector, gets defined in terms of something you may not have intuition about, module, which is a total mistake in teaching. So what we'll do instead is imitate some really good teaching by Gilbert Strang. We're going to teach vectors concretely. Now, Gilbert Strang has been the preeminent lecturer and professor in teaching linear algebra for years. This is an older book of his I adore, but I know he has newer books and newer videos that are just fantastic. Now, in his teaching, notice he starts with a concrete example, the vector 1, minus 2, 7. And that's what vectors are. They're just ordered lists of numbers. Now, this vector he called three-dimensional, and the idea is a vector represents a displacement, that it says it is 1 unit from the origin in one direction, 2 units from the origin in another direction, and 7 units from the origin in a third direction. And we'll get to a concrete example where we show what we mean by this. But also, basically, the vector is drawn as an arrow from the origin, which also could be thought of as position 0, 0, 0, to where its head is. So that basically, the vector is only described as the displacement from the origin to its head in some abstract geometric space. Now, you and I can possibly visualize 1, 2, and 3 dimensions, but vectors could have any number of coordinates, and they would then have abstract dimensions. Again, this is something we'll get concrete about and show that how this isn't a problem. So let's take a completely implementation operational view of vectors. To a computer scientist, a vector is just a mapping from an interval of integers to some floating point values. This is an overly specialized definition, and it puts the vector very near the data structures that often implement it, which would be the list or array data structures. Now in Python, this vector 4, 4, 2.5, it would map the integer 0 to the 4, because Python starts indexing at 0. It would map the integer 1 to the next 4. It would map the integer 2 to the 2.5. And we see in the Python example us going at that third entry using the number 2. Now, again, we're using the square bracket notation to build the vector in Python, and then another instance, the square bracket notation to dereference or access the cell, or the coordinate, or the value. And we call these values that are just numbers, scalars. Now in R, the vector is built up by the C command instead of the square bracket notation. And again, in R, we start indexing from 1, not 0. So the third entry is labeled 3, not 2. So again, in both cases, we see how the code constructs a vector and how we get access to that cell. In data science, we largely use vectors for their ability to hold numbers, which is kind of mundane. Though we care about vectors because they're an incredibly useful data structure, they're a component of many other data structures, and we'll talk a little bit more about it. To get back to the vector's mathematical properties, which we do use in data science, and we'll demonstrate this in a concrete worksheet later in this lecture, we expect, just like mathematicians expect, the vectors to be additive. And again, we can take the vector 1, 2, 3 and add it to the vector 1, minus 1, 0. And by definition, this is implemented as corresponding cells add up, i.e. the first cells of each vector are added to each other, creating a new first cell of the result vector. The second cells of each vector are added to each other, creating a new second cell of the result vector, i.e. the 2 and the minus 1 become a 1. And then the third cells are like the 3 plus 0 becomes a 3. This is what is meant in computer science by vectorized code, that we issued the command to two vectors, not writing a for loop over every cell, and we expect all these operations to be performed for us. It could be sequentially, or it could be with a accelerated vector processor, such as is in our CPUs, or it could even be parallel, which may be in our GPUs. So the fact that we kept our hands off and just said, do all of this, and didn't overspecify with a for loop how to do it, is the grace of vectorized notation. We also expect some convenience notations. We expect multiplying by a scalar, as we show in the 10 times column, to perform the same multiplication to every cell, and we expect adding or subtracting a scalar to again do the same operation to every cell. A very common operation done in vectors is called the dot product, and it's written as two vectors with a dot in between them. And we're showing this with the vector 1, 2, 3 and the vector 4, 4, 2.5. And the definition is we multiply all pairs of like cells. So we do 1 times 4 for the first position, 2 times 4 for the second position, and 3 times 2.5 for the third position. And then we just add up all those terms. So corresponding cells are multiplied, and then the whole thing's added up, as we show here. In Python, the notation is done by the dot function, and in R, it's done by this inline %* operator. We can also dot a vector against itself. This operation is called the Euclidean 2 norm squared, i.e. the square root of the dot product of a vector against itself is called the Euclidean 2 norm, and it's a measure of the size or magnitude of a vector, and it's a very standard geometric measure. Another operation we can take with vectors is the mean, and it has a very simple definition. It's just add up all the cells and divide by how many cells there are. And just to relate this back to earlier ideas, that is equivalent to dotting our vector against a vector of all ones and dividing by the count of the cells. For pairs of vectors, there's a natural distance measure. There's a number of distance measures, but the one we'll use is the sum of square differences. And it's defined as we sum over all cells, the difference in cells between the corresponding cells and the vectors, and square it. But it turns out that is just the difference in the vectors dotted against itself. This is the Euclidean distance, or it's the Euclidean norm of the distances. Again, a difference, again, squared. Again, the interpretation is 0 means identical, large values mean we're experiencing large differences. In contrast to a distance measure or metric, we also have something called a similarity measure. A similarity measure, in this case the Pearson correlation coefficient, this is 1 when vectors are identical and smaller numbers when they're different. So it's measuring a degree of likeness, not a degree of distance. Again, this formula for it looks hairy, but it's built up from smaller pieces. All it is that saying that the two vectors' similarity is the dot product of each other against each other, but again, it's shifted by the mean. So we take the mean off each vector and dot them against each other, and then everything in the denominator is just renormalization. But it looks like it's the similarity of the x to itself times the similarity of the y to itself. So it's saying the Pearson correlation coefficient is just how similar are these x to y compared to how similar x is to itself and how similar y is to itself. This, going back to the mathematical idea of defining things in terms of their properties, is a little clearer to understand if we slow it down. From the above formula, we can see that the correlation coefficient has a large number of invariants. It's, for instance, invariant over swapping the roles of x and y because it's symmetric in the formula. It's also invariant to adding a constant to every cell, the same constant to every cell, because we subtract the mean off everywhere x is. Therefore, if we added 7 to every cell, the mean would get 7 larger, and then it would again take that off. So, and then the third invariant is it's also invariant to any positive multiple because x appears with the same dimensionality one time in the numerator and one time in the denominator. The square root undoes that squaring of dotting against itself. Therefore, if you multiply it by 10, you get the same correlation because it gets divided out. And again, we say only for positive numbers because the sign is in the numerator but not in the denominator due to the conventions of the square root and the squaring. Now, another way of saying everything we set up to now is if x was such that it was already mean 0, and x dot x was already 1, and same for y, y was already mean 0 and y dot y was already 1, then none of these transforms we're talking about would be needed, and we just get correlation of x to y is x dot y, relating it back to a previous idea. So it's probably easier and a quicker formula to not use this large formula to compute dot products, but in fact just to shift and rescale x and y to this standard mean 0 unit norm form before computing the correlation. So notice how each idea is a small extension of earlier ones. It might have a large formula, but there's a small number of new ideas. We'll try to make this more concrete by working concrete examples, both using geometric objects and then also running code in R or Python. The point is that anytime in data science, when you see a hairy formula, that's not for you to implement. That's for some package to supply to you. So it's not, yes, it hurts somebody, but hopefully it won't be you. Now, again, I think that repetition is what people call understanding, or familiarity built through repetition is what people call understanding. So I'm going to repeat concepts in different contexts to give you a chance to make them physical, and then you might want to replay this whole thing, because certain concepts that may have been abstract early on may have more concrete founding for you later if you were to review this material. So let's move on to a demonstration. So let's build up some physical intuition of vectors by using physical measurements of physical objects. Here is a light box that is maybe about 4 inches by 4 inches. Here's a heavier box that is approximately 4 inches by 2.5 inches. The yellow bars are 4-inch measurements, and here we're denoting the width and the height of the lighter box by 2 yellow bars. We're denoting the width of the heavier box by a yellow bar, and then a white bar to denote the lesser height. Now again, vectors can store any numbers, doesn't have to be just heights and dimensions. So here we're going to estimate the weight. We say this is a 2.5 ounce box, and the smaller box is a 4 ounce box. And again, we're going to use the yellow to represent 4 and the white to represent 2.5. So it's the same number, though in different units. Now we're going to encode this as a vector. We use that cap to denote the origin, these connectors to connect up the units. This is like a number line, as we learned in grade school. And we can tell which segment's which because they have a first, second, third relation from that cap origin. We can do the same for the other box. And what's going to be different is who's first, second, and third. So these are the vector representations of 2 of the spatial dimensions of each box plus the weight. Now notice we've lost the units and we just have these representations. We can make this a more random access structure where we can pick out one measurement without having to step through all the others by recording each measurement in a different dimension. Here we introduced the second measurement is at a right angle to the first, and the third measurement is at a simultaneous right angle to the first 2. So that's a new representation of that large light box. And the idea is we can measure off any one of those dimensions without the others just by calipering that thing in the appropriate dimension. Its width is its width, its height is its height, and the weight is that third dimension. Here we're re-encoding the other smaller, heavier box. And again, notice that we're careful to preserve the order of the segments and use the same dimensions for each of these 2 representations. So these are 3-dimensional vectors, where again, each displacement is in one coordinate after another. We're emphasizing that each vector has a different height and a different displacement in this third forward dimension. Now we're using a bit of string to denote the net displacement of the vector. Obviously, each vector is a sum of each of its displacements in each coordinate, but really it also is a net displacement in space. Now, we're seeing 3 dimensions, but 100-dimensional vectors might have a net displacement in the abstract 100-dimensional space, which obviously you and I can't visualize, though we will visualize it later with a scatter plot. What we're going to show is most of the information of the vector is the length and the angle from its origin. And so when it comes to comparing vectors, we think mostly about magnitudes and angles. And in the correlation, we're abstracting out the magnitudes to get down to the angles. So let's go back to our data on the boxes. So we can record a bunch of facts about box 1, the larger, lighter box. For instance, we measured the width as 4 inches. We measured a height, which again was just the back depth of the box, as again 4 inches, and we estimated the weight as 2 ounces. Sorry, 2.5 ounces. Now for box 2, we can record its measurements. And again, in this case, it was a width of 4 inches, a height of 2.5 inches, and an estimated weight of 4 ounces. We can lay this data out into an organized structure called a data matrix, where each row is an instance we're very much interested in, and every column is a possible measurement. So it's like a database schema. All rows have the exact same set of possible columns, and each column is in the same units for every row, though columns can have different information in different units from each other. This data structure presents us with a number of vectors. For instance, any one measurement type is a vector, which we could call a column vector because it's oriented as a column. Though we can leave out the row or column orientation of a vector as a non-important detail, as we just did, as we extracted out heights as a column, as a vector. We can also extract a row as a vector, as we do here. What we're going to do is next show in a worksheet how we can use these datums and calculate over them. Even though the data may come in from a spreadsheet, it is vectors in our mind. Now let's work examples of all the concepts we've discussed in R. So first we will start up in R Studio, and we'll load the data from a comma-separated values file. We'll take a look at the data, and you see it's 2 rows, and the name of the box type is written in the instance column, and all the values we discussed, width, height, and weight, are values in the additional columns. We can examine the types of the different columns, the column names, and as we said, we can extract a column, which is then a vector structure. You see, it's a vector that has a 4 and a 4. We can also extract a row, either by 1. This is the first row because R starts numbering at 1, not 0, or we can extract the row by names if we have remembered to set the row names. So now what I've done is I've moved the values from the instance column into row names and cleared out the instance column, which then lets me select rows by name, and also now the columns are all just the values. The name is no longer in there. Though for most analyses, I prefer not to use row names. And we can now do what we said we'd do with vectors in the very start. We can extract the value cells out. We can divide by a number to make every value simultaneously half, and we can even do a vector difference, showing the difference in each corresponding measurement between box 2 and box 1. We can define a function to compute the mean square difference, and we see that box 1 looks a lot like box 1, and box 1 differs by box 2 on average of 1.5 square units, though obviously we have both inches and ounces, so it's a fairly abstract units. We can build a function to make them unit magnitude, so just rescaling, no shift. And then in this notation, the dot product is the cosine of the angle subtended by the 2 vectors. So this 0.9, it says they're very much parallel. We can also do a shift to mean 0 by subtracting off the mean from every entry of the vector. And then we can divide again by the magnitude. That just gives us now a copy of the vector that is both mean 0 and unit magnitude. And as we see, the dot product of box 1 against itself is 1, and the dot product of box 1 against box 2 is negative 0.5, expressing the fact that in the new shifted versions, most places where box 2 is going up, box 1 is going down, so they have a negative correlation. And that is indeed the dot product of these shifted and scaled vectors is indeed the Pearson correlation of the original vectors. We can also plot the representation in two ways. The first way, what we've done is we transpose the data such that each box is now a column. Normally instances are in rows in the data matrix format, but now we've transposed it, so each of the two boxes is a different column, and each different possible measurement about them is a different row. So we've reversed the roles of instances and measurements. However, this format where every row is an instance and every column is a possible measurement is in a critical format called the model matrix. So in this transposed format, we can see that the width is 4 for box 1 by reading off the x-coordinate, and it's 4 for box 2 reading off the y-coordinate, whereas the weight is 4 for box 2 and 2.5 for box 1. So we can see where they agree or disagree on measurements. Now, the more traditional scatter plot omits the instance names, or the names of what we're doing. And so again, perfect correlation would be dots along the line y equals x. So we see these features disagree and this one agrees, but we don't have any notion of which is which as we did in the previous plot. And that's it. That's a worked example of how vectors are an integral part of data in data analysis. Normally the column vectors are all the measurements of one feature across many individuals. In a row is all the measurements of one individual across a moderate number of features. And that concludes my lecture on vectors in data science. I hope what you take away is that they're largely a data-carrying data structure, that we don't quite use them in the same sense mathematicians do until we want to compute similarity. And when we compute similarity, we bring in all those mathematical concepts we had earlier in this lecture to do that. And also, I hope you now appreciate that scatter plots, which you might see everywhere, are actually graphical representations of how similar two column vectors in a data matrix are. And now usually two columns in a data matrix are two different measurements across all individuals. So usually in scatter plots, each dot is an individual and the coordinates are the two measurements. However, as you saw when we transposed the data matrix, we can use that plot to do other things, like show for two individuals how many different measurements they agree on. And again, the usual measurement of that is a correlation, and under certain circumstances, and most definitely for the dot product, the whole point is to reduce these complicated notions of similarity to something simple like the cosine of an angle. Treat vectors as directions and just treat that simple planar angle, not even anything very complicated, just the angle in the plane subtended by the two vectors. Treat that angle as the measure of similarity, or the cosine of that angle again. So small angles have a large similarity. And then all materials for this lecture are shared here on the GitHub, including the CSV or comma separated values file that the data was stored in, and then the worksheets that ran all the code to do this. Well, thank you very much for your time, and I hope you enjoyed this lecture.